So for part 2 here, we'll get rid of this integration by parts. We'll just move into 8.3. You guys, keep working and catch up to me as necessary. What happens in 8.3 is what I might call, or the book calls it, trigonometric integrals. So a bunch of trigonometry here. Trig, I'm just going to call it trig integrals. By the way, which is different than what's coming next. Up in 8.4, 8.4 is a process called trig substitution. That's an awesome process I'd like to teach you, but I'm going to wait a day or two. But that's trig substitution. So I guess before we do that, we got to get kind of good at some trig integrals. So watch this. This is, you could have done this without me. You can do, you're smart. I think you can do this integral. You didn't necessarily need me. I could throw this on an old Cal 1 test, but it would throw some students off. But there's no real new great techniques here to teach you. You know how to. I'm trying to say you could figure this out. Do you have any idea how to do an integral like that?
No, you take out a sine.
I don't know what you mean by take out a sine. You can't take out.
Take it out, but like out of cube.
Oh, good. Well, the sine is cubed. Yeah, there you go. So if the sine is cubed, maybe you want to...
substitute the cosine squared.
Well, not yet, no.
Sine squared and sine cosine?
No, you're thinking too hard, actually. You can just do U-substitution and do this problem.
Yeah, you separate the sine squared and sine, and then U is equal to sine, correct?
Well, okay. Usually, when you do U substitution, the U is inside of something, like it's inside a square root, or it's inside something being cubed, or it's inside a trig function, like the little 2x is inside the trig function. But right, so I see this as, you're right, here's another thing. We all need to be sophisticated enough to realize that sine cubed means sine of 2x cubed. It does mean that, but we write sine cubed. Right. But that thought might help you. I want to let u equal sine 2x. And I'm so happy, and I think that's so great, because what's du? Cosine 2x. Is that perfect or what? Right? Don't you want, when you let u equal something, you want your du to wipe out the extra junk. That's one way I think of it. I want, the derivative is cosine 2x. Chain rule says times 2 dx. Right, you guys? I'm happy. I'm so happy. Here I go. When I replace this stuff, here I go. I'm replacing it. What is this? What is this?
U cubed.
U cubed. Thank you. It's U cubed. Okay, what is all this extra crap out here? Basically, it's my du. Except for this extra 2 here. I need to deal with that. How do I deal with this extra 2? I like to move it over here and call it 1/2 du is equal to this cos 2x dx. So I am replacing the underlined cos 2x dx, I'm replacing it with what? 1/2 du. See, this is a replacement game. This U substitution is a replacement. I pull the 1/2 out front, and I put the du right there. I think some students think U substitution is magic. Like, where the hell did you get the du? It's not magic. Everything gets replaced according to the substitution that you declared. Everything gets replaced according to how you declared it. So, cool. Can anybody integrate a U cubed? U to the 4th over 4 with a 1/2 out front. So 1/8 u to the 4th plus c. Oh, but what's u? A sine function. So 1/8 sine to the 4th of 2x, I guess. So, this is new. This is up in 8.3, but I'm using old school techniques of U substitution. And then it can get worse, of course. Here's one. Yeah, let's work on this one a second. You know, I think what I just learned from this one is that if I don't care how many damn sine functions I have. If I have a bunch of sine functions, I can call it u. I can let u equal sine, and du will be my cosine. So it's nice to have a bunch of sine functions and a cosine sitting on the end. Because then you can let u equal sine, and du will wipe out that cosine. It's nice to have a bunch of sine functions with a cosine sitting on the end for your du. You're going to let u equal, or by the way, vice versa. A bunch of cosine functions and a sine function on the end works. So I want there to be a cosine function out on the end is what I'm saying. I'm saying I like that. So I call this game, I made up this word, I call this game odd man out. Yeah. I want to put that odd guy, that cosine cubed, I want to put one of them out on the end. So here I go. I'm going to call this is sine squared. And so I'm going to break this and call it a cosine squared. And I'm taking the odd power and I'm putting this one cosine out on the end here. You guys with me? Yeah. The cosine cubed is now a cosine squared times a cosine. See, when you take the odd power and put one of them out on the end, it leaves you an even power. If it leaves you an even power, you can turn sine squareds into cos squareds, and you can turn cos squareds into sine squareds through your most famous identity, right, which is your most famous identity.
Sine squared of x equals 1.
Your most famous identity that says sine squared plus cosine squared of x of an angle, if the angles match, equals 1. That's your most famous identity, but there's two other versions of it. If you wanted to solve for sine squared, what would it be? 1 minus cos squared. If you wanted to solve for cos squared, what would it be? 1 minus sine squared. So what was I saying a few minutes ago? Yeah, listen, I said, damn it, I wish I had a bunch of sine functions and a cosine out on the end. So I put my cosine out on the end, and now I want to take the rest of these cosines and I want to turn them into sines, because I said I want a bunch of sine functions and a cosine on the end. So I'm going to take this cos squared and turn it into, according to the formula, cos squared is 1 minus sine squared of 4x. This is out on the end. This sine squared is still here. And now I am ready to do the appropriate u substitution. Do you know what the appropriate u substitution is? Let u equal sine. Yeah, sine of 4x. Why? Because du is the cosine of 4x, which is beautiful for my problem here. Hang on, sometimes I gloss over the details. What's the derivative of sine? Cosine of 4x times 4 dx. Okay, all right. Dude, I'm so happy. You guys don't seem as happy as me. Here I go. I'm ready. I knew I was ready, so I did this u substitution. Now I'm going to substitute it all in. Watch. What is this thing here? It's a sine squared. What's that? That's u squared. Multiplied by these parentheses. These parentheses have a 1 minus sine squared. What's that? 1 minus sine squared is 1 minus u squared. And then what's out on the end here? What's this cosine? What's that? That's my du. And she said it right. She said it was 1/4 du. Right? I mean, technically, I got to watch out for this 4 here. You're right. 1/4 du replaces cos 4x dx. Right. Right. So I replace that with a 1/4 du. Woohoo! I'm so happy. Did you catch that? That was cool, man. That was cool. I played this game, I called it Odd Man Out. I put the odd one out, left me an even power, which I could turn into sine squared, and left me a bunch of sines with a cosine on the end. A bunch of sines with a cosine on the end is classic U-substitution. And I'm very happy, and I'm pausing, and I'm acting like I'm happy. I mean, hopefully you can finish this. I'll help you finish this. It'd be a shame to screw it up now. Do you know how to finish this?
Yeah.
Distribute, then integrate. Yeah, thank you. Distribute, then integrate. Some people still try to integrate first. It's terrible. It's terrible. You distribute, then you integrate. So it's a 1/4. I distribute. It's a u squared minus a u to the 4th. And now you integrate. There's nothing to it. It's a 1/4 out front. How do you integrate a u squared? 1/3 u cubed. How do you integrate a u to the 4th? 1/5 u to the 5th. Plus c. And we should plug back in our u's. What was it? We should plug. I mean, we're done. But we should plug back in our u's. You can distribute the 1/4 or not. I don't care. I don't care, man. What is the u, though? What was the u? Sine 4x. So it's the sine cubed of 4x is what that is. And then this is 1/5 sine 5th of 4x. Yeah, there's the answer. It's a process. Again, I don't know, maybe you needed me to help you, teach you about this process, but there's nothing new here. I mean, it's good old U-substitution, but I'm manipulating and playing with these trig identities and these trig functions, you know? Yes?
Yes, yeah. Could I replace sine squared of 4x with 1 minus cosine squared of 4x, then distribute, and then separate, and then do each one? Would that work?
No.
No? Okay.
So, remember, if I got these sines and cosines, I'm doing, and they're powers of sines and cosines, then I'm going to let u equal one of them. If I let u equal a sine, what do I want out on the end for my du? A cosine. So from what you just actually asked me, I don't think you got anybody out on the end there. So what I would like is a bunch of. So I've only done 2 examples. So, but the game here is if you can get yourself. And here, I'll do another one. Watch this. Let's do this.
I don't know, I need the sine.
So I'm telling you, I want somebody out on the end. And if I decide to put a cosine out on the end, what do I want the rest of the crap to be? Sines. I want them all to be sines.
Yeah.
So I want a bunch of sines with a cosine on the end. Or vice versa. A bunch of cosines with a sine on the end. Because then I can do a u substitution that completely turns it into u's and du. I mean, maybe you don't quite see it yet. So on this one, the truth is, what did I say? My game is odd man out. So you could play this one, play this game either way. Do you want to put the cosine on the end? I would. I'd put the cosine on the end. So I'm leaving him alone. I'm going to call this cosine to the 4th and put one of those cosines out on the end. Now that means I put one out on the end to save him for my du, which means I want all the rest of this crap to be sines, because I want to let u equal sine, and that'll be my du. So I want all this to be sines. How do I get all this crap to be sines? Well, a cos squared is, I mean, this is how you turn things into, so this cos to the 4th is actually like a cos squared, and so that cos squared is 1 minus sine squared, What is this out front? This is sine cubed. What is out on the end? A cosine function. So what have we done? We did what we wanted. We took this thing and we manipulated it. We put a cosine function on the end and we turned what's left into sine functions. Did you follow it? And this time, you know what, the first couple problems I did, I had a 4x and I had a 2x, and that spit out a 2 and a 4 or a 1/4, or you know what I mean? This time I don't have that, so this is a little easier. What would you let u equal?
Sine of x.
Sine of x, that's the point. What's du? Cosine of x, dx. Okay, cool, no extra 2's or 3's on this one. This is fairly nice. I'm gonna leave this one hanging here. I want to show you something else. But here, I'm going to leave it hanging after I replace all this. When I replace all this, what is it? U cubed, I guess. Right? U cubed, what's this?
1 minus u
1 minus u squared. That's all multiplied. What's out there on the end?
du.
Du. Dude, look what you got. Look what you got. You ain't got no trig. You ain't got no trig. You replaced your trig. You substituted your trig for u's. These are polynomials. Now you got to do this right. You got to FOIL it all out. You got to FOIL it all out, distribute, and but then you can integrate. Easy, because it's power rule. Okay, I'm going to leave that hanging. I want to show you this problem. I could have done this problem differently. I'm calling this game odd man out. Because they were both odd powers, I could have put the other one out. Let me show you what I mean. In other words, I could have put one of those sines out there. This would have been sine squared. Hey, rather than finishing, I know you want to finish your problem, don't you?
Yeah.
Hang on. Rather than finishing, try to pay attention to me here, because I got a point to make. You can finish that later, I think. So,
I already did.
look what I just did. I'm saying this integral can be done another way, is what I'm saying.
Right.
I could do the other odd man out. I could put the sine function out on the end. Okay, hang on. I put the sine. You follow me?
Yeah.
Okay, so now if the sine function's out on the end, I'm saving him to be the du, which
Right.
means I want u to be cosine, which means I want all this crap to be cosines, which means I'd like to turn that into cosines. I can do that. Sine squared is a 1 minus cos squared.
Yes, that's good.
So there you go. There you go. Bless you. And I let u equal, now what do I do now? U equal cosine. Now this is one of the funny things that's different here is that what's the derivative of cosine? Negative sine x. So it does, this is beautiful, but it does spit out a negative sign.
Right.
That you better keep track of. So here I go, I replace it, it spits out a negative sign, and I'm starting to replace this crap. Here we go, what is this? 1 minus u squared. What's that there? U to the fifth. And what's this crap on the end?
Negative du.
Yeah, du with a negative sign I've already put out front. That's right, that's right. Cool.
Got it.
So here's what's interesting. Yeah, if you I warned you, FOIL this out and distribute and do this and integrate, please. And when you're done, you're going to replace all your u's with what they were. What were they?
Sine.
Sines. All right. Same thing here. This one's a little easier. You don't have to FOIL it. You do have to distribute.
Right.
Distribute. Integrate. After you integrate, you're going to replace these u's with what they are. They're cosines. Your answer is going to look way different than this answer.
Yeah.
But they're equivalent. They're equivalent. This answer, they're going to look way different, but they're equivalent. They can be proven to be equivalent. This will have a bunch of damn cosines in it. This will have a bunch of sines in it. Can't you relate sines to cosines through these identities? And so if you wanted to prove that this answer looked like this answer, you could go play a bunch of trig games. But that's not the point. You know, I wouldn't. They're going to look totally different, but they're equivalent. And that happens in trig, because trig functions are related through identities.
Must have fun grading it then. What's the right answer?
I know, I got to do it twice. Right. I got to do it both ways so I can
Plus.
check students who might choose some other way. Right. Either way is good. I mean, this one, you know, the truth is, what was better, maybe? Maybe this second one was better.
I like this too.
I mean, there's less foiling involved here, right? This guy, right, I still got to foil this. There's a little more algebra here, just a little. There's a little less algebra on that one.
Do that.
I guess it might be time to go. So I'm at the beginning of section 8.3 here, teaching you about trig integrals. And we just dealt with sines and cosines with odd powers. There's a whole nother story if they have even powers. If they have even powers, we got a little different story. I have to teach you that. And then they do a whole thing about, what about secants and tangents? How do you handle those? Oh, great. And then they do a whole nother thing about cosecants and cotangents. How do you handle those? So there's kind of a lot in section 8.3 here. It's all involving trig. The truth is, I kind of leave out the cotangent, cosecant thing. But I like to have a secant tangent discussion with you. All right, I'll see you Friday, I guess. Thank you.